Okay, we finally got our AV working, even in advance of conscious computing and the singularity being reached, which is outstanding. So it's an honor to have Manuel Blum with us today. This is probably one of the more exciting titles we've had in a few years, toward a conscious AI. You know, many people in the field of machine intelligence are here through a pathway of being intrigued, curious, and surprised by the existence proof that somehow machines are generating the states that we feel, this awareness, subjective states, the pains and pleasures of life, being here. And it always seems like such a mystery to even begin to breach that topic, at least to do it in a credible way without getting in trouble and being called something that you don't want to be called, like, oh, that's far-reaching, it's flaky. And I think the hope has always been for a long time that there is a science to be had in this space, because surely something is going on, and it's something we do not understand yet. Manuel is the Bruce Nelson University Professor of Computer Science at Carnegie Mellon University. He's a 1995 Turing Award winner that recognized his work in theoretical computer science, in particular his work on complexity theory, cryptography, and links to program checking. He got involved in thinking through brains, I think, even before you go interested in complexity theory, is my guess from looking at your bio.
Right.
So Manuel actually came to MIT in the mid-1950s, and he pursued his passion about understanding thinking and brains by working in the famous neurophysiological laboratory of Warren McCulloch and Walter Pitts, of the famous McCulloch and Pitts early paper, which happened probably in the 40s. That paper was written 1943, that basically wrote down some basic constructs of what a neuron, a symbolic, abstracted neuron was like, and how you'd program and look at the behaviors of assemblies of these units. And his interest in brain and machines led him to think through applications, or motivated or framed his interest in mathematical logic and recursion theory for the insight it gave to him on brains and thinking. And he went on to do his doctoral work with Marvin Minsky, did his PhD in 1964, and then went off to UC Berkeley as an assistant professor of mathematics, came to Carnegie Mellon in 2001, and he's had many incredible students over the years, and continues to do groundbreaking work. I personally hope that your work on consciousness and links to computational architectures will break some ground, because it's still a big mystery to most of us.
I hope so. Thank you. Thanks very much. So let me start by saying something about how I got into this. When I was a kid, I was a very dumb kid. And my teacher told my mother that I might be able to get through high school, but don't expect I can get through college. So I really wanted to be smart, and I asked my father, so this must have been first or second grade, I asked my father something, I wanted to ask, how do you think? But I asked, how do you memorize? Because I had trouble memorizing, and he said, well, you just do it. And that didn't help very much, and so I kept pestering him until at some point he said, if you understand the brain, then you'll be able to think better. And I thought, wow, what a great idea. I liked that very much. So we could fast forward, let's see, to when? So I was thinking, I remember when I was in 6th grade, about trying to think about this conscious brain, what it was like, and I just didn't get anywhere. You can try to think about how that brain is working, and you get a sense, or I got a sense anyway, that there was like a little person in my brain that was looking out of my eyes. And I knew that then I'd have to understand the brain of that little person, and this didn't make a lot of sense. So that was too bad. And then when I got to MIT, I took a course on we went through the 20 volumes of Freud, because that was the closest I could get to brains then. And then McCulloch and Pitts came to MIT, and I was told by my teacher of Freud, Richard Schoenwald, I should go introduce myself to him. And it's McCulloch and Pitts, they are my real mentors. They're just terrific. McCulloch and Pitts, as you had pointed out, Eric, is that they defined the formal neuron very early. A formal neuron, very simple neuron, which could add and subtract inputs and compare the threshold. And they basically told the neuroscientists of the time, there must be inhibition, not just excitation. Because, if you have just excitation, you have monotone circuits, you cannot. And they said, nah, we've never found inhibition in the brain. But they insisted it's got to be there, and sure enough, they did find it, as you might imagine. So that was great. Okay, so that's where I'm coming from. So I was a few years in this in their neurophysiology lab. Besides McCulloch and Pitts, Jerry Letvin was there, and another person that was there was Pat Wall, who was especially interested in pain. So you'll see pain coming up here in this work. So let me get here to where I can see what I'm doing. So let me start by saying what is consciousness. So we have an idea, roughly speaking, consciousness is what you're aware of, what you see, what you hear, what you smell. Another thing that is part of your consciousness is your inner speech. You all speak to yourself all the time. You are speaking to yourself. And I'm absolutely sure that my dog is speaking to itself. The difference that I speak English and my dog speaks Dogish. It's a different language. But it is speaking to itself because you need that speech in order to plan, to be able to make plans. And I can see my dog planning where he's going to go each day and stuff like that. You're also conscious of your dreams. You're not conscious when you're not dreaming, but when you're dreaming, you are conscious of your dreams. And that's another example, and your feelings, joys, fears, etc. So what's consciousness? I'm still talking about what that is. So this is going to come up. Have you had the experience of going to a party and seeing somebody whose name you know, but you can't quite come up with it? And it's embarrassing, isn't it? I'm always happy when Lenore is with me. Oh yeah, I should have mentioned. This is joint work with Lenore and Avram. And Lenore is a very important part of this project. And in fact, she's going to be in Beijing in November giving this talk. So you'll be able to see. You have to get it from me. You could get it much better from her, but that's the way it is. Anyway, so you're at a party, you see someone whose name you know, and you don't remember it. So, it's embarrassing. You go and get yourself a glass of wine, you speak to somebody else, and then half an hour later it pops into your mind. Where's it coming from? Some computation has been going on in your brain that you are completely unaware of to cause that thing, suddenly that name, to pop up into your brain. So we'll talk about that. Dreams, selective attention. The reason for that picture is because you have the sense when you see that picture that you see the whole thing. But I don't know if you saw the dog that's there or the doghouse in that picture. Or anyway, there are all sorts of things you don't see. You form an impression, and that impression, the vision people call it the scene gist. And there's nothing more than a couple sentences. It's enough. It's in Brainish, of course. It's not in English, but it's enough for you to then be able to dream about that. And in your dream, you will see something that's very much like that. So it's incredible. It's there, but the gist of it. Problem clarification and problem incubation. The mathematicians talk about the fact that you really need to get very clear the definitions and the statement of the problem that you're working on. And clarifying the problem is something that you do consciously. The problem incubation then is sort of like that name coming up. Your unconscious part of your brain is working on it, and that's the incubation part. And if you play ping pong, you know that to learn to play ping pong, you must pay attention consciously. But if you play ping pong, you know that in a tournament, you take your consciousness offline. You do not, you let your unconscious do the work. And so that's example. Here are some quotes from Hadamard, Poincaré, Gauss, again showing how the unconscious is coming in. Hadamard, on being very abruptly awakened by an external noise, a solution long searched for appeared to me at once without the slightest instance of reflection on my part. Poincaré, you know the story of his stepping up on the into a bus, and at that moment a solution to a problem came to him he doesn't know from where. And look, also from Gauss, after years of failing to prove a particular mathematical theorem, finally succeeded by the grace of God. Like a sudden flash of lightning, I myself cannot say what was the conducting thread, which connected what I previously knew with what made my success possible. The point of all this is that that unconscious part of your brain is a very important part of your brain, is doing a lot of the heavy lifting here. So what is consciousness? So what I'm going to present in this talk is, what I want to present is a formal model of a Turing machine, something that we call the conscious Turing machine. So let me mention that when I first learned about finite automata, I was so happy that finally a finite automata could be a model for the brain. You see, I had no model other than this homunculus. Didn't make any sense. And then finite automata was a possible model. And then it was nice that Plato, actually that was Plato's model of the brain. He points out that he thought that we are born with the knowledge of every language that there is in the world, or that even that there could be, and that our job as young kids is to find our way to the state, which corresponds to the language that everyone else is speaking. Again, this is a little, we know it can't be that. And then I learned about Turing machines, so that was much better. But it still didn't get to the problems of consciousness. What I want as a mathematician is get to that, a good model, which I call the conscious Turing machine or conscious AI. And then if it works, after formalizing the conscious Turing machine, we'll define consciousness in that model. You know, what's consciousness? Who knows exactly? Well, this will give you a definition and then point out properties of that consciousness in the model. So let me make the point that when I talk about consciousness, I mean consciousness in this model. Then there's the real consciousness. That's another thing. And don't think that I am not trying to get a model of the brain. That's very complicated, too much for me. I want a very simple model that will be enough for me to understand consciousness. Okay, so after formalizing this, we'll define consciousness and then point out properties of the consciousness in the model. And let me just say that the quality of a formalization and definition depends largely on how closely the notion squares with what you think it should be, and whether or not it helps you understand the concept. So you'll have to be the judge of whether this is a useful notion or not. Okay, so let me mention here, too, that our model is inspired by the works of cognitive neuroscientists, psychologists, and philosophers. I'm lucky that at CMU, John Anderson is, that's interesting. John Anderson and Alan Newell were both very interested in this question, and John Anderson is still at CMU. The work I'll be talking about, the model that I'll be basing it on is work of Bernard Baars, Dan Dehaney, and Kevin O'Regan. I have David Chalmers as a philosopher, and Bjorn Merker is an important person because he's the one that basically thinks that you don't even have to have a cortex in order to be conscious. For him, the consciousness comes from the from the midbrain, which actually is what McCulloch thought too. So anyway, the easy and hard problems. So this was defined by Dave Chalmers. You know what the hard problem is? The easy problem is to build a machine that simulates something like feeling pain or feeling joy. The hard problem is to make a machine that really feels the pain and the joy. And you might wonder, well, why do you need to do that if you have a good simulation? But I'll explain why. Let me get to that first, saying that Chalmers' definition is a lot more general than this. He's interested in all qualia, definition down below. He's interested in a lot broader stuff. I am going to be restricted to pain and joy, and this talk will just be pain. Lenore's talk will just be joy. So she doesn't understand why I'm interested in pain. I don't understand why she's interested in joy, but that's okay. Our research and this talk is restricted to understanding pain and joy. Yeah, you'll see how he comes in. Thank you. Including the extremes of agony and ecstasy. And we have a reasonably good answer for pain, and we have only a partial answer for joy, for how these feelings are generated. So before we get into that, I'm a theoretical computer scientist. I don't go in and cut up brains. I saw Pat Wall do this with cats many times, but I personally don't do this. I'm theoretical computer science. What can I do? So I'm looking for a simple model of consciousness, not a complex model of the brain, but a simple model of consciousness. When I talk to John Anderson, he says evolution abhors parsimony, which apparently means that it's complicated. The brain is complicated. And then Lenore points out mathematics thrives on it. We need simplicity. So our aim is to propose a simple model that we can understand and prove theorems about. We want properties of consciousness to be emergent, not programmed in. This is one of the things that consciousness will does for us, we believe, is that it enables you to deal with complicated worlds that were not expected in the first place. And you'll see why in the model that should be expected. So the easy and hard problems, I've told you. What's the difference between the simulation, which we know to do, and the experience, which is what we're trying to capture with consciousness? And I'm going to explain this to you by describing a disorder called pain asymbolia. This is a very interesting disorder. People who have pain asymbolia, don't look up asymbolia. It has to be pain asymbolia. It's a very particular thing. People who have pain asymbolia, you can pinch them, prod them. They know where you're pinching, how hard you're pinching. If there are temperature variations, they know if it's hot or cold. They know everything you know about the pain, including very severe pain, but they don't suffer. And the young girl that has pain asymbolia, you prick her and push her, and the doctors come around looking, and she giggles because she knows how strange this is, that you can do these things. And so after pinching and pricking, then she'll show, yeah, try here, try that. So, okay. Pain asymbolia, they know about it. They don't suffer from it. See, our robots, we know how to build pain asymbolic robots. What we don't know how to do is build robots that really feel the pain. And that's what I would like to be able to do. There are two kinds of pain asymbolia. In one, the girl giggles. In the other, you can see her grimacing. And it looks like she's feeling the pain, but she's not. The great thing about these kids, I don't know if you've ever tried this. You take a frozen bottle of Coke. As long as there's some liquid in it, you can hold it without getting frostbite. You try to hold it for as long as you can. I can never manage very long. It hurts, really hurts. These pain asymbolic people, they know it's frozen, but they can hold it for as long as you want. No problem, even though they feel it. Okay, so consciousness has to do with the architecture of the brain. The architecture presented here deals with the brain at a very high level of abstraction, a level way above that of neurons. So even though McCulloch and Pitts were the first to define the formal neuron, no neurons in this talk. We're trying to get at a level even above that. I love the neurons, and I love what's being done now, but I'm trying to get up to a level slightly higher. And as I said, the architecture is not obvious. You know, I just could not, I was trying and trying to get a model that would give me some insight into how that brain works. You know, it bothered me that we're born without a manual to tell us how the brain works. Isn't that, I mean, okay, well, anyway, it bothered me. I wanted to have a manual, and basically, when I went to see McCulloch and Pitts, and I said I would like to work on consciousness, I was told, you may not work on consciousness. No, that's it. And when I pushed for it, Walter Pitts came over and said, well, you know, you got this much skull to get through. EEGs will give you just a very broad idea of what's going on in the brain. You can't get any good data. Forget it. So I wasn't allowed to think about consciousness. It was great that that there is something that we were allowed to think about it in 1990, because that's when fMRI came on the scene. So, okay, so I think fMRI came on the scene in 1990, and at that point, Bernie Baars came up with his model of consciousness. So let me tell you what this will be sort of fundamental to this talk. This is Baars' theater of consciousness. It's a beautiful model. He views consciousness as the activities of an actor on the stage. So it could be several actors, but usually it's just one or two, not very many actors on the stage. And everything that actor is saying is being viewed by these audience members, who are the processors of the brain. You have 10 to the 11th neurons. I think of the brain as having like 10 to the 11th processors. And each of these processors has a different purpose in life. And they are listening to what's going on the stage. So up on the stage, what's the name of this person? And then down below, somebody's coming up with the name. So the conscious self is not privy to the workings of the unconscious self. I've already told you about what's her name. Anyway, right? So this is going to be something, red going up, green coming down will appear in the model. You recall when you first met that person. It gets broadcast, so the entire audience knows that you want about that. So first the question is, what's her name? And then that's broadcast. Then maybe some from the unconscious, something about what she does, that gets broadcast. See, it comes up, and then it's broadcast so all the processors know about it. And then another one speaks up, her name begins with a T, that's broadcast. And this business of broadcasting this information eventually leads to a half hour later, her name comes up from the audience, which has been thinking and searching to answer that. So next up, let me give you Baars' model as he published it. This is it, his model of consciousness. It's, you can see input on the left, vision, hearing, touch. Output on the right. There's a central executive up on top that's controlling stuff. There's a working stage. I call it short-term memory, but the cognitive psychologist calls it working memory. And then information goes down, and there are many, many processors down below in your unconscious. Here's perceptual memory, autobiographical memory, etc. Okay, so what can I'm a theoretical computer scientist. What can it contribute to the discussion? So first of all, a well-defined formal model. That's what I want. A good formal definition of consciousness. I want that. Explanations how agony and ecstasy might arise in a machine. I'd like to have that. Understanding for distinguishing simulation from experience. You can already see, you can get beautiful video, YouTube videos of a robot that's afraid of the red ball. And it's doing everything to make you think it's afraid. It's clearly afraid, but you know it's a simulation. What's the difference, and how do you tell the difference? And one of the points I want to make is that without an understanding, there's no way to tell if an entity, an animal or a robot, is conscious. You need to have some understanding to be able to say whether it's a simulation or it's not. One of the reasons it's important, here's something that comes up a lot. Medical doctors, physicians would like to be able to know when the person comes in and says, he's got this tremendous pain in his shoulder that he needs to have those pills. Does he really need to have those pills? Or is he just trying to get pills so he can sell them on the street? How do you tell even? And it's amazing that there are no good ways to tell yet. I mean, even the fMRI does not yet enable us to be able to tell. It's very strange. So one of the things I might hope as an outcome of this would be a way of being able to distinguish the person who's simulating the pain from the person who actually feels the pain. Okay. So next up, the formal definition of the conscious Turing machine. Okay, so let me make a point again before I bring that up, that the purpose of the conscious Turing machine is not to compute uncomputable functions. That's not possible. Nor is its purpose to compute functions more efficiently. So I teach this undergraduate complexity course, and that's mostly what complexity theory is about, is how do you compute and efficiently. That's not the problem we're dealing with. The purpose of this model is to suggest possible solutions to the hard problem. So here's the model. So this is the beginnings of the model, and I am trying to keep it as simple as possible. You'll see a few things. There's an input on the left, there's a short-term memory in the middle, and the output on the right. And notice they're not connected here, and they will not be. And then there's this tree, which connects the root node at short-term memory down to all the processors in long-term memory. And no central executive, in fact, in this. We started off, we did try to follow Baars' model, but the central executive did not make sense. And I'd have to talk to you about why and what that is, but it's kind of nice that if you must have one, you could imagine one of these processors down at the bottom being the central executive. But anyway, this tree will represent that anything that's up on the stage gets broadcast to all the processors below. That's the green arrow. And then information from the unconscious processors goes up to the stage. There really should be two different trees. There's one for the stuff going down, and there's one for the stuff going up. But it's too complicated, too messy, so I'll just show you one tree. And let me point out the difference between these, that information from the stage going down to the processors, that goes fast. I'm sure Koch thinks that this is much too simple. It's a binary tree, but even a binary tree will work. It just gets you to a lot of nodes very quickly. And so in the model, it's just a binary tree. And it goes very fast because the green arrow is taking information down to a node, and all that node does is to push it in both directions, and then it gets pushed until it gets down to the bottom. Very fast. There it is. Going up, it's another story. So this took a while, and this is where Avram actually comes in, will be coming in. And I'm very happy about one thing. In trying to create the model to go up, you basically have these processors needing to talk to each other. One processor says it has important information to get up there. The other one has important information. Which one gets up there? The short-term memory, or the working memory, is very small. George Miller talked about, have you seen his paper, The Magic Number 7 plus or minus 2? He pointed out that you can store very, very little in that short-term memory. And the question is, and one of the questions I'll try to answer for you is why that is, in fact, necessarily so small. Anyway, going up, there was a question of how will these processors talk to each other. It can't be anything very complicated, and it took a while for us to realize it can't be anything more than like a comparison of two numbers. And that's what's going on here. It's just a comparison of two numbers. And these numbers are chosen, so there's a pain process. Actually, there are many pain processors, but my elbow has a pain, and so anyway, these processors, the pain processor for the elbow, it itself assigns a weight to the process, to the information it has that it wants to get up. It assigns that weight. And for the pain, it's pretty easy to understand. It's all determined by how many nerve fibers, how many nociceptor fibers are firing, and at what frequency. That determines the weight. And there's for joy, there are ways to, these things go up, and at some point, maybe pain at -5 and joy at +3. What happens here is pain has the greater magnitude. So pain is what will go up, but the weight it takes up with it is the sum. -5 + 3 is -2. Yes?
In a prior experience with some sort of pain, does it change the weight?
Yeah.
It makes it less or more?
Yes, yeah. Yeah, you'll see. Very good question. I hope you'll see that's in fact what Avram's secret experts problem is all about. But for now, let's just get this clear. -5 + 3, -2, pain goes up. Pain at -2 and fear at -5. Again, the one with the greater magnitude, in this case fear, goes up, and it goes up with the sum of the two. Okay? And now, it turns out that the sign of what's up there at the top node, at the root, the sign of whatever is up there is actually the sum of all the weights of stuff below. So you have to think about that, but it's the sum. And if it's positive, it basically means that you've got something positive going up there, and if it's negative, then you've got pain or some fear or something like that going up there. Okay, so, trying to show you what happens as pain and joy change, things move, change around. And in fact, in this model, this is a picture. I found this frying pan. You see the fire down there. And the intent here is to show you that things are bubbling down at the bottom. And because this is constantly going on. There's constantly stuff going on down there. Yeah.
Does this mean you can only feel pain or fear at once, but not multiple things?
Yeah, so that's interesting. You'll either feel the pain or you'll feel the fear, but the weight will be an accumulation of these weights. And that's something that you can test. That presumably you can test. Now you have to understand that because of this bubbling, you can go back and forth between pain and fear, and that will come up also. Or you can come up, you may have many pains, but any one pain, you only, according to this model, you only notice one of them, but with the weight of all of them. Okay? And, and another point over here is that you see this triple over here, address, information, weight. This is the information that's carried up to the top. The pink, the information, is the actual chunk that's in your short-term, in your working memory. That's what you know about. But for various reasons, you need at every node to have both the address of where the information came from, the information itself, which is this very short description, like of the house, of the gist of what it is that's supposed to get up there, and a weight, which you may or may not be aware of. It's the information that's the chunk. And here is the complete model, pretty much. And still, external input is not connected to short-term memory. Oh, let me just mention something else here, as long as we're here. Here are some experiments you can do. You can ask, according to this thing, if you have severe pain and real pleasure, they should cancel if they're about the same. So, wow, that's kind of interesting. Have you ever been to a dentist and had laughing gas? It's a wonderful experience, let me tell you, laughing gas. So the dentist is told, you give enough gas so that you don't feel the pain. But because if you give too little, you're going to be feeling the pain. But if you give too much, then the patient will be bouncing off the walls, and you won't be able to keep him or her down. So you've got to give just the amount where they balance. And that's essentially what this is suggesting, that when pain and joy are about equal, they should not get up there. Okay, here's the model. Let me just mention, you see these lines here, that there are 10 to the 11th processors down there. If you link them all up, these are, as you'll see, they point in one direction or the other. 10 to the 11th squared is 10 to the 22. You're getting very close to Avogadro's number. You cannot have all those links. It's just not possible. So there's a question of, well, how do you decide which links go in? Maybe some of them are built in, and in fact, that is the case. Some of them are built in. But by and large, what happens, I think, and in the model, is that some processor asks the question, what's her name? And another processor comes up with the name, and that's sort of saying there's information flowing from one long-term memory processor to another. And if enough information flows in that direction, that will grow a link from the one that asks, that has the information, to the one that asks. So these links would build up and with time. Okay, let's keep on going here. Here's another thing that comes out of this model. Notice that the input is still running, yes? You notice that the input does not go directly to the working memory, and the working memory does not go directly to the output. Everything is via this long-term memory down below. So information from the input can come down and go directly to the output. This happens like when you're have you had the experience? You touch a burning hot stove and your hand pulls back, and you know that you're not consciously pulling the hand back. The information is going up to your spinal cord and then back down. I used to wonder, why does it go so far? Why don't it just go up to the wrist and back? But you don't want to do this. You want to really pull the arm back anyway. So, but notice, you are not conscious. You're not consciously involved in this. It's going down and it's going right back up to the output. So that's the model. In some sense, what's going on in short-term memory is looking over what's going on in long-term memory. It sees what's going on. It gets some information from below, and it broadcasts it. According to this model, you become aware of that burning hot stove after you've already pulled your arm back. And it's kind of nice that that's actually the case. Yes, Daniel.
How would you explain something like Korsakoff's, where you've got an individual?
Like what?
Korsakoff syndrome. So it's a person who has
Right.
short-term memory, but loses the ability to lay new long-term memories down.
Oh yeah, HM.
Yeah, exactly.
Yeah.
So here it's implied you have to go through long-term to get to short-term.
Well, he did have he did have some capability. He just didn't have the capability of putting new memories down there. But those processors were still working, and he could make use of the old memories. I don't see that as. But
So the processors can still run; they're just not updating the memory.
that's right. They're just not updating their memory. Okay, so there are many details here, of course. Yes.
Previous slide, the red links you mentioned how they formed, but do they go away after some time, or otherwise there's just monotonically going to be more red links?
See, there's this stuff happening. Oh, you mean the ones down below?
Yeah, the down below.
So in this model, each time a question gets answered by a processor, that begins the process of generating a link. And if the link is generated, in fact, that may take the conscious part completely out of the picture. You sort of learn to play ping pong, and then you can leave the conscious out of it. It's handled totally unconsciously. Yes.
It's also related to emotion machine and society of mind. Because Minsky also says has this idea of inhibition at the level of emotions, and he also doesn't have a central executive.
Whose model is this?
So this emotion machine from Minsky.
Does the emotion machine no central executive? I should read Minsky.
Well, what of the Society of Mind?
What?
What of Minsky's Society of Mind?
Oh yeah.
At least the model there reminded me it was lots of little cognitive machines floating around, and there's a broadcast model, and machines are sort of like much more of a distributed process than the orderly binary tree manner of connections back and forth here.
Yeah.
It's a really notion of lots going on with a broadcast, and opportunistic solutions. That's very similar.
Yeah.
What he doesn't think about is, I think, the asymmetry of the downward broadcast at a low bandwidth, fighting the way back to the.
So he has this book called Emotion Machine. That he is
Yeah, he does have the emotion machine. Yeah.
I'm an old timer, so I read the old book. Yeah.
So there he's talking about emotions fighting each other. So you can shut off some emotions. If you're in love with somebody and you're in the honeymoon phase, and you can stop thinking about all the bad things about that person. Like your mind just shuts off some of the processes.
Yeah, so here I was talking about pain and fear and how they cancel each other. I'll have later, okay, let me keep on going here. So, details. Let me just mention that another story that I'll get to here is, have you read Oliver Sacks? He's a wonderful writer. Really worth reading, just terrific. And Oliver Sacks, he talks about, he likes to hike. He talks about going up into the mountains on a hike. And he got to a field, a fenced out field, and the sign, "Beware the bull." And he looked, no bull. He walked into the field. And he says he was just ambling along very nicely, and all of a sudden he saw the bull. And the bull was getting up on its haunches. So that scared the living daylights out of him. He turned around and ran as fast as he could out of that field, and only noticed once he had left the field that he'd actually torn a ligament. Torn several ligaments. It was a very bad tear. He was in the hospital for more than a month after this. But basically, the fear took over. And it's only once he's out of that field that the fear subsides, that the pain can get up there. And that will be part of this model here. Anyway, the details. How the processors choose weights. So a pain process. In the case of a scraped knee, it's the weight. Its weight, the absolute value, is proportional to the number of fibers that fire and the frequency of their firing, as you might expect. a context processor. It has a relatively high fixed weight, high enough to keep its information, what's called the scene gist, on stage, except when concentrated attention is required for the task at hand. And if you really are concentrated on proving that theorem, you may very well forget where you are in doing that, because you need that memory for other things. A task that has been put off, its weight, so you ever have the experience, you have a test at the end of the week or something, and you're not too worried about it, but the next day you're a little bit more worried, and then a little bit more worried, and so it goes, and these weights increase with time. The closer you get to the test, the greater. Details. There's a threshold for allowing processes into the short-term memory. This is kind of interesting. We need to be able to talk about a threshold for allowing processes into short-term memory. If set too low, that threshold is set too low, then ideas just bubble up. Ideas that you haven't thought about that well bubble up, and you have the case of mania. People that are in the manic state have lots of ideas, none very well thought about, and they're kind of bouncing off the walls. If the threshold is set too high, there's no ideas. There's an absence of ideas, and I call that depression. It's just no ideas. It is depressing to not have any ideas at all, to be in this world. So, and here's something else that comes up in the dynamics. When processes enter that short-term memory, they slowly lose weight. We need an equation to see how that goes. They slowly lose weight, and when they are kicked out of off the stage, they slowly regain their weight. So this is going on all the time, and it means that if you have many processes of about equal weight, they'll take turns. One will go up, it'll be dropped, another one will come in, and you may cycle through them. Or if you have, as you were pointing out, you have several pains, you'll be aware of one, then of the next one, then of the next one, and it will keep going around. That leads to cycling, and this is processor A links up to B when A answers B's call, and this is what I've talked to you about. What's this? I haven't said very much about what the long-term memory processor itself is. Important thing is that each processor down there gets inputs from other processors, from the short-term memory, from the external world, and gives outputs also to those places. There are the links. One thing I haven't mentioned is the interrupt, and that's very important, that it is possible to have an interrupt. And this became important in thinking about that extreme pain you have when you tear a ligament. You have that extreme pain. What is causing that extreme pain? And the answer, in part, is that extreme pain will interrupt all of the processors. It's different from broadcast. Broadcast, the input is like a typical input that you have from the world, which you may or may not pay attention to. An interrupt basically forces the processor to put everything on the stack and to pay attention. Maybe just for an instant, but it has to pay attention.
Why do you need this exception? Why isn't it just something with a very high weight? So it takes over the
Yes, so we were talking about that, and I don't have an answer for you, yes. My answer for that extreme was the interrupt, but you might be right, and I hope that you're right, because that means I can simplify this. That would be nice. Yes? For anything, yeah.
Directly puts into the internal from the external world and out to the external world. Before they were all mediated by
Well, the short-term memory is paying attention to what's going on. The input from the external world can come down to a processor, and it can talk to another processor, and it can go right up to the external world.
the tree started, the root of the tree was the tree.
Yes, that's separate from the inputs coming down to the processors and the inputs going up. whatever's in short-term memory also has this tree to get down and information can get up. They're separate.
Yeah, there was nothing direct. It's wrong.
I think I would like to talk to you about it. Okay, well, details of the dynamics. This is where Alvin comes in. So the thing I really liked about the reason that Alvin got into this is I mentioned that there is this model that we have where you're just comparing numbers and going up, and that's basically what Alvin was looking at with his sleeping experts. His theorem presents an optimal algorithm to dynamically refine weights assigned to information by competing processors. So an important thing here is that each processor decides by itself how important some information is. Some information is more important, some is less important. Each processor decides for itself. But you know, some processors could be very optimistic and they think that their information is the most important of all. And what this algorithm does is it lowers the weight, the value of those weights. And another processor may have very weak, or maybe sort of not so sure of itself, but it has useful information. Maybe it'll be raised. So this sleeping expert's theorem is just what one wants for making sure that these weights are treated properly. Okay, so there's this algorithm. By the way, it's in Foundations of Data Science, which you cannot buy at Amazon, but you can get it for free for the web. Alvin Blum's name was just attached to it. Blum, Hafcroft, and Canaan. Consciousness. So recall that consciousness in the model is the content of short-term memory. How reasonable is this definition of consciousness? I mean, why should that be consciousness? That it's what's in short-term memory. That's what we're defining conscious. See, the formal definition. You are consciously aware of what's in short-term memory, nothing else. Why is this at all like what we sense as being conscious? And the answer is that all of these processors are aware of what's going on in that short-term memory. The reason it feels the way it does is because every single processor in your brain knows what's going on there. If your consciousness were due to even just one of those processors, you would be conscious. But it's the fact that all of them are getting that information. And that stage activity can be persistent. Many questions. Why is short-term memory so tiny? Indeed. Why is short-term memory so tiny? 7 plus or minus 2. Nowadays it's 3 plus or minus 1, but that's okay. You got the idea. Plus or minus 2. And our answer for it is that you want all these processors paying attention to the same thing. If you had a large memory, you could have some processors paying attention to this and other processors paying attention to that. And you don't want that. You want them all paying attention to exactly the same thing. And what's a chunk? Yes?
I think it's somewhat related to the neurons we have.
Probably. So, you know, computer could be smaller, yeah. And maybe our computers could have a larger short-term memory because they're so much more. Although it's interesting, you know, how would one of our large computers compare to the brain? Did you know that the Titan computer has a number of transistors just about exactly equal to the number of synapses in the brain? So it's, anyway, we won't get into that. Why is short-term memory so tiny? What is a chunk? The chunk is just that information that gets up there into the short-term memory. I think of a chunk really as being like a pointer. You remember that it consists of an address, information, and weight. And the important thing to me is that a chunk is like It's the information that you're conscious of, but the address is the pointer back to where that information came from. And that is what a chunk is. So the psychologist said, when George Miller defined chunk, he said, well, a chunk is a digit or a letter, or it could even be the alphabet, if you know the alphabet. Well, the point is that the chunk is a pointer to where that alphabet is stored. And you can now reel off A, B, C, D, E, F, G, right? You know the alphabet. Isn't it interesting that the brain figures out what data, how to store the data, what data structure to use? How come the alphabet A, B, C, D, E, F, G is stored as a singly linked list? If you want to go backwards, very hard. I tried at some point to memorize going backwards. I could do that. I made up a ditty, Z, Y, X, W, V, U, T, S, R, Q. But it doesn't matter. You can make up a ditty and learn it backwards. And what I discovered was there's a singly linked list going forward, and I have a singly linked list going back. I don't have a doubly linked list. I can't tell you what comes before P without going forward. Anyway. So why am I interested in consciousness? Well, it's obviously useful to humans, right? I mean, we are conscious. It's useful to humans. And I think it's useful to a lot more animals, not just humans. It focuses the LTM processors on creating the current best interpretation of the world. We are constantly interpreting that world, and it's a checker on that interpretation. There's some wonderful examples where, one eye sees Einstein, the other eye sees Lincoln, and you keep on going back and forth between Einstein and Lincoln, and the brain is confused. It doesn't know which one it is. It's a checker on the interpretation that you have. And it gives the entity the ability to solve unanticipated problems, to deal with a complex world using all the tools at its disposal. I think that is really very important for this. The ability to solve unanticipated problems. We want to have that. And this model does that by basically giving the important information to all of the processors and having them all work in parallel. Okay. So I already talked to you about this. An example about what's her name. I talked to you about Oliver Sacks. Dreams. There's something interesting that I won't get into, but I kind of love this, so I will tell you. Do you have your hand up? No. So if you saw that picture of the house, you can recall it, right? You can close your eyes and imagine that upside down house. Or maybe better, you can recall the front door to your house, what it looks like and everything around it. But it doesn't. That recollection is not the same as seeing the actual thing. Just not that strong. And you can dream about the front of your house, and when you dream about it, it will look like what you see. It will be much more like what you actually see. Wouldn't you, as an architect, want to be able to imagine and see exactly what you would really see, at least in a dream? You'd like that. So one of the questions that comes up is, why not? And it's I'll give you my understanding. There was a time when I really tried to remember my dreams, and everything was just fine. I could manage to be able to remember more and more, until at some point I realized I didn't remember if what I saw was real or just in the dream. I couldn't distinguish. And at that point, I realized you don't want to remember your dreams. And I stopped trying to remember them because I couldn't tell. And I'm sure that I think that our visualization, which an architect would surely want to be able to do, our visualization is also not so good not as good as what we can do in our dreams, because then again you would be confused between what you're actually seeing and what you're imagining, which is essentially what happens in schizophrenia, where you hear things or see things that aren't there, and these people are confused. Okay, where are we?
the deep assumption right now that quote unquote people imagine things. Let's talk about where that comes from in architecture.
You want to talk about
Imagination.
imagination?
You said, well, you know, you have to, you're sort the process of imagination, and forget about what that is right now. We discriminate that from reality. Let's talk about imagination for a second in architecture. Imagine is probably powerfully important in our ability to do counterfactual reasoning and to create the world of civilization, to imagine what is not in the world now, but to imagine
What could be?
what could be. What's going on with the LTM and the architecture for that? That'd be a dinner conversation.
Yeah. I clearly will not be able to answer that now. Let's see. I think I'm past overtime already. So I'm going to go fast now. One of the examples was grasping the well-understood proof of a theorem. You know how with a theorem, when you've understood the proof, you feel like you got it inside your hand. But actually what you got is a node at the top. And this is square root of 2 is not rational. What you have at the top is the proof starts with the square, assume to the contrary that the square root of 2 is a over b, ratio of 2 integers. And the fact that you can follow this thing down to anything you want is what comes up out of this thing. Okay. Oh God, I was going to be talking to you about this. The hard problem. So consider the hard problem for the special case of pain. How might the conscious Turing machine experience pain? So we tried, let me just say that we tried many explanations. We, Lenore and I, tried many explanations. Here are suggestions. There are many that don't work. As attested to, for example, by the asymbolics, pain might arise from observing unconscious reactions such as grimacing, crying out, and such. But the asymbolic 2s do grimace and cry out, but it doesn't bother them. So it can't be just that. Response to painful situations, such as a finger pulling away from a flame, which you're not aware of till after your hand is pulled back. Sweat and increased heart rate, muscles that vibrate. You know, these are things that might be causing the pain. They are not. They are not behind the pain because there are people who do this stuff, but they don't suffer from the pain. So here are the suggestions for extreme pain. The first is broadcast. Extreme pain is an actor that takes over all short-term memory. It prevents all other actors from reaching the stage. Pain messages and only pain messages are broadcast. Every processor knows of the pain. So in the case of Oliver Sacks and the bull, fear got up there, and fear refused to let anything else up on the stage, and so he didn't even notice the pain that was being caused. So that's part of it. Another part, confirmation. So this. Let me just mention that there are many things that this model predicts, and there are some things that it does not. Clearly, I'm not telling you about the things it does not, because I just want to give you the positive view of this thing. Anyway, confirmation of this business. Under conditions that produce great pain, asymbolics can think while normals cannot. You can become asymbolic by getting a conch on your head as an older person when you already know how to play chess, and even under great pain, you can still play chess perfectly well, where you cannot. Under great pain, you cannot really play a good game of chess. Here's another thing that I call a confirmation. In a Darwinian design, you might expect pain to lead to construct. You know, if you're in great pain, you need to think. That's important to be able to think. What kind of a design is it that under extreme pain, you cannot think about anything else? The statement is that extreme pain comes about from pain on the stage not letting anything else up on the stage. How can that be? And it's kind of anti-Darwinian. You might expect pain to lead to constructive thinking, but agony actually inhibits constructive thinking. It forces you actually to rely entirely on your unconscious self. Is this confirmation? I don't know. Yes.
Yeah, I mean, I can disagree with that because I feel like when you're under extreme pain, under the Darwinian design, your mind do everything you want to avoid it. But if you're in agony and if you're like ruminating on those experiences, then you're actually trying to extract pleasure out of it because you're giving yourself pity, and if you give yourself pity, you find happiness from it. So
From extreme pain?
yeah. So in every way, you're doing whatever you can to escape that pain. So that's my thesis.
You can imagine many explanations. So one gives an example. In evolutionary history, if someone was in extreme pain, better to get rid of them. Social maximization. Leave them on the side of the road. Try to be unknown. Selected for. Another would be a deep and urgent call for social contact and assistance. That's more valuable than solving the problem yourself. You can imagine these kinds of socio-biological explanations to go to the tribe.
Okay.
We can imagine we can come up with an interesting
Yeah. I will. Okay. Okay. So, our suggestions for sudden extreme pain is interrupts, but already you've told me maybe we don't need these interrupts. Interrupts which suddenly cause everything to put everything on the stack and then pay attention, which is different from broadcast. Broadcast, it's sort of an input that you can pay attention to, but interrupt, you're forced to put everything on the stack.
But jumping out of the box, could somebody say you have this conscious Turing machine without qualia?
Oh, yeah.
Why do you need the actual experience? We have a mechanical design for all this beautifully well, including the way you set up the broadcasts, without ever being there.
Okay, so again, the argument is that absolutely every processor in your brain is aware of what's going on there.
Right. I can imagine a machine built by Maytag doing that. Right? I mean, sort of wire it up. I mean, there's still kind of an interesting conceptual leap that I think we can make as the listener to going from mechanical design with communication with every possible Avogadro's number of processors listening. So why does that lead to the experience that human beings have of actually having subjective qualia? Now, it might turn out that somewhere there's a missing definition that says it is the same thing, but it's unclear to me.
Yeah, and I'm claiming that that's all you need. Now, we can very well disagree on that.
I just don't know. I'm saying I don't see the actual.
The only problem I have is that when I say that every single processor knows about what's going on there, that's subject, that if any one of them is responsible for consciousness, you will be conscious of that. But I still have not answered your question. I agree.
I guess here's the thing. I was sitting here wondering if the young version of Manuel Blum, sitting thinking about the homunculus, came back now, would he be satisfied, or would we look at this as another computational homunculus?
He would be satisfied because this actually answers lots of questions I had. I mean, it's much better model than the finite automata. It does answer a lot of questions. And yes, there are some cases where it doesn't seem to be right. But as I pointed out, if pain and joy have about equal value, then they cancel each other out. There are things like that, many things like that seem to be answers. Anyway, here's the instant shock of pain, the hard problem for joy. Won't go into it. That's Lenore's thing. Then there's free will, a beautiful explanation of free will. What? You're way out of time.
That's very important.
Should we let people go and then we can talk about it?
So we started about a little bit late.
We just okay. So
We usually ended 4:30. I've only ended 4:40.
no, this will take 3 minutes. We'll be fine. I'm saying that free will is not a problem, and I was very happy. So my explanation, which goes back to the chess, I like this as an example, is you know, if you're playing chess, you find yourself in a position that you have to make a move, and you don't know whether you should move this piece there or that piece there. And you don't know which you're going to do until you've done some computation to figure out the result of them. And you have free will until you know you have free will to choose what to do until the moment arises that you've figured out which move is better, and then you give up your free will to make the move. So that's my explanation of free will. And then I found this wonderful explanation by Dehaney, which is exactly what I'm saying. He says, our brain states are clearly not uncaused and do not escape the laws of physics. Nothing does. We're okay with that. But our decisions are genuinely free whenever they are based on a conscious deliberation that proceeds autonomously without any impediment, carefully weighing the pros and cons before committing to a course of action. When this occurs, we are correct in speaking of a voluntary decision, even if it is, of course, ultimately caused by our genes. We have free will because we are only aware of what's going on in that short-term memory, and the long-term memory is just a huge collection of apps, and we don't know how they're working, and we are open to whichever possibility turns out to be important, better. Yes?
So the act of deliberation is not a finite state machine.
The what?
The act of conscious deliberation.
The act of...
Finite state machine. Because you're saying that act of conscious deliberation is the
Well, it's actually, you know, in the case of chess, you have some processors, probably several processors, that are evaluating the result of these moves.
Is that evaluation or?
Oh yeah, I'm not saying that there aren't finite automata here. There are finite automata. It's just that the brain itself is not to be viewed as a finite automata. You can't. It doesn't make sense to say that you know every language in the world when you're born, and you just have to find a particular one. Anyway, that's the end.
So we have a mic for the capture. Any questions? I can't believe there's actually questions after all that. Okay, so.
I had a question about why you have different processors for pain and joy and fear. Aren't these all like functions of the same thing? So I can take joy as the negative of pain and fear as probably future predicted pain?
Your brain, at least, has processors for you know, you have your brain, your entire brain is responsible for pain, and it knows about pain in the elbow. It's a different processor that knows about pain in your hand. There are lots of different processors that are concerned with pain.
Okay, but I can't say that.
And lots of different ones concerned with joy.
Yeah, so I can't say that joy is the negative of pain and then use like a different processor.
You're asking about why some are positive and some are negative. That's built in. Pain is built in. It's negative. That's easy enough to have it built in. Joy, it's perfectly possible to have it built in as positive.
Yeah, so I had a follow-up on the Emotion Machine. So the Emotion Machine was a book that was never published, but it was online by Marvin Minsky for a few years. We all had to go through it as part of effective computing class. And one of the things he brought out, he argues, is that for the long time, you know, mankind uses these umbrella words to describe things that they don't understand. So for instance, he says consciousness is an umbrella term that we have kind of agreed to that exists. It's similar to, you know, the term that physicists coined ether to explain, you know, the propagation of waves in vacuum.
Sure.
Right? And how do you know that consciousness is not an ether? It's something that doesn't exist, but we basically have, you know, worrying about it before, you know, because we can't explain.
So I mean, this is fine. You understand that I'm just talking about consciousness in the model. I define consciousness to be what's in short-term memory, period. That's it. That's what you are consciously aware of. You're saying, well, different people have different notions of consciousness. Yes, that's true. But in this model, that's what I take to be consciousness.
Yeah. No, what I'm saying instead is that the whole the exercise in defining consciousness might be trying to define something that does not exist.
But it does in the model.
Is it correct?
It's just a math model, right? So
I'm curious how attention fits into your model. So I can sit here and I can visually scan my body from my toe tips to my head, looking at my knees, my elbows, and like experiencing the pain or comfort at each thing. So where would that plug in to the model? Is that short-term memory, or where does attention fit?
Yeah. So some actors. So the actors that are up on the stage are pulling your attention together. What's her name? Or this scene. Did you see the dog in the scene of that house? It's some actor up there is paying attention to some part of that scene. So that's coming from below. There somehow that actor that has that question has managed to get up on the stage and asking the question.
Sort of a module then below.
Way down there, which has finally managed to get up there. And there are many different modules that would like to have attention on different things. Some people are interested in vision, other processors are interested in hearing, and so on. So it depends on which one finally gets up there.
I feel my personal subjective opinion is that attention is in the conscious part, but because I'm deciding that, okay, I'm going to pay attention to my big toe and how it's feeling right now. Now I'm going to go pay attention to my elbow and my shoulder and feel how sore it is. So,
and I'm saying that comes from below, okay, that you decide.
Since I have the mic and I have a question, I'm going to ask it. So you talked about distinguishing whether somebody is stimulating pain or actually has a pain, whether the person who asks for the pills really has a pain. So do you have any suggestions towards that?
For deciding whether it's simulation versus the real thing? Yeah, I sort of already suggested it when I said that a person who is really feeling it cannot think, whereas the person who's simulating it can. That's the pain asymbolic.
Last question.
maybe just Mike, give me the mic. Just go for it.
Have you created a model for the computational model or implementation of the robot yet?
What I have is I have Mark Wegman at IBM Watson wants to build this, and I have a Chinese collaborator, Wang Hongxi in Harbin, who is started the process of simulating it. This is just starting. Until now, my interest has been mainly making sure that the general form of the model is correct for what I want.
Yeah, I would take on the Turing test. I think that's
Yes.
First off, I just want to say thanks for coming to speak to us about this.
It's been a pleasure.
Really intriguing. Something I am curious about is how did you and Lenore arrive eventually at this model, and were there other intermediate models that you considered but tested out and didn't work?
Yeah. I have lots of slides about things we considered and then got rid of. Part of it was trying to make sure we have enough that we can explain a lot of stuff, and part of it is making sure we don't have too much, because I was so happy when I was able to get rid of stuff. Like, for example, Bernie Baars talks about a processor down below getting up on the stage, but these processors don't actually move. The processor doesn't get up on the stage. I'm saying that the only thing that gets up on the stage is that little bit of information that it wants to put up there for processing. And so I initially I needed to use the pointers to be able to say where it's coming from and who has the stage. I've managed to get rid of all of that. So yes, there were many models along the way, and it's sort of settling down now, sort of. Yes?
Yeah, so it's an interesting model. There's just one thing that kind of bothers me is this idea that everything can be put on a single positive, negative axis. If you look at it seems like there's a lot of emotions that don't just fit to positive or negative, like
Absolutely.
curiosity or emotions.
Absolutely.
So how would you imagine those trading off? If we're feeling pain and curiosity, do those actually trade off?
Yeah. So it's sort of easy when I talk about pain and joy because clearly one's negative, the other's positive. But what about curiosity? It could be a positive thing, it could be a negative thing, and it's really the processor itself that's deciding the weight is also deciding the sign.
But this idea that you can add the weights of things that don't really seem like they would line up, like that you're adding.
Yeah, it's kind of nice though that in the end, what's up on top is the sum of all the weights at the bottom.
Sure. So like just taking two different vectors, adding them together, so you just have some, and then whichever one is higher magnitude, that's the one that's different.
I have the microphone now. So, sorry, just for the question. So, it just seems intuitively to me, and we'll talk more about this over dinner tonight, that it's not just a push, but a pull model from executive. And I know it introduces a complexity, but this would capture notions of value of information, notions of the fact that of a singular experience, which seems to be on the stage in the conscious part, is not all just little information bits, but this idea that you're actually also broadcasting, but pulling, and actually even pulling with addresses. It's not just all push from excited neural apps, but it's a pull too from executive. And I'd love to see that added to your model. I think it's going to be needed. Just what again?
Yeah. And I'm hoping you're wrong, but okay.
Why is it just a broadcast?
Why not just a broadcast?
The push is just a broadcast.
Yeah, but now push is a broadcast. Fine. My sense is sometimes there's an integrative approach across all the pushes which might define a context or a state that then does a pull, an active pull among resources, right? So maybe the idea is you can have a broadcast of a pull, of a need, right? Not just a perception, but an actual attentional signal, right? So it's a coordinate. There's this idea right now that seems to be part of this model that you have a listening short-term stage that's where that's integrating and listening into stuff being pushed and some sort of scoring mechanism bringing stuff up, which is great. But the sense is that once you have integration, that's not the end of the story. That's part of the building of a picture, which might not just be all push built, but pull built.
Yeah, sorry, I meant pull is a broadcast.
Yeah, but now we're hearing about a pull broadcast, asking for certain things, right? Requesting certain help, resources.
That's what it is in the model.
No,
So it will get, if it gets up there.
He was broadcasting out all sorts of perceptual information, right?
He was broadcasting something from the top that says like, does anyone know this person's name? Please tell me.
That's your request.
Oh yeah, I see. Does anybody know? But as opposed to directed with an address.
So if you are in a jungle and you hear a tiger sound, and all of a sudden you are looking around yourself, if you see the tiger, because now the short-term memory problem is trying to pull.
You pull with index, not just general broadcast, right?
All of a sudden
Unless
you're really paying attention to
there's some special property of the broadcast that gives you some efficiencies. I think there's more going on in executive than
You're going to have to explain push-pull.
If you broadcast, everybody gets it, and whoever has information.
with high efficiencies. Yeah. Yeah. Okay, so we probably should. We'll just.
Yeah,
we'll end there. Thank you very much. I think your father will be proud of your answering his question. We're trying to. That he asked you, how does the brain work?